Hi, welcome to our third lecture of Physics 121, Energy and Environment. This is our first one talking a little bit more, so not the broad strokes of the first week anymore, right? Now we're starting to get into some of the details here, right? And the details that we're getting into is really, well, the whole subject, physics. Trying to understand a little bit of some of the definitions that we work with typically in physics, how some of those things might apply, at least laying the groundwork for that right now, right? When we started to talk about stuff like engines, for example, we need to understand how it starts from some sort of fuel source like gasoline and ends up as motion of a car. There's some steps in between, and we're not going to get all of those today, but we are going to start to set up a lot of the terms to describe them. So, I like to start with this picture. Of course, we can tell there's a source in this thing. I am stealing this from somebody else. But it does a neat little job of showing some of the different things going on in physics or how we categorize the fields. So the left side of this over here, talking about classical physics. Classical physics is really what you think of typically when you're thinking physics. Right, if you want to know about Newton's laws of motion, all of that is within the realm of classical physics. Most of the stuff on a day-to-day basis is classical physics. What separates these, and really kind of where it starts to break down a little bit, our first hint that classical physics wasn't necessarily all there was out there, is actually still kind of included in here, electromagnetism. Because electromagnetism was initially not supposed to be breaking classical physics. When we were first working with electromagnetism, we understood it initially as two separate things, electricity and magnetism. And we knew they were related, but we didn't exactly understand how. And it wasn't until we really started to get to the end of electromagnetism to where we're at in our understanding of it now with James Clerk Maxwell highlighted down here, bringing together what we now call Maxwell's equations, even though he didn't actually come up with any of them, but there are four equations that describe everything in electromagnetism, and they were the first evidence that classical physics didn't quite work. And that was a really neat thing. That was actually what defined the speed of light. That's when we had practically solved out electromagnetism. And that discovery right there was really what led into some of these other areas like relativity into quantum physics. And you'll notice here, relativity and quantum physics, we both understand those fields by themselves quite well. But this chasm between the two is very intentional. It's highlighting this fact that quantum physics and relativity don't behave very well together. Right? Not at all, actually. We can understand how very small things work. We can understand how very large things work, and we understand both of those separately pretty well. And when I say very large and very fast is the other part of that, actually. But when something is very small and very fast, that's kind of where it's in between these two, and that's right smack dab in the middle of things that we just don't know about yet. And I highlight this to really say that physics isn't done. There's a lot of work ongoing. It's not just, working with new materials or anything else like that. There are still many fundamental questions we have in physics that we're still working towards. So there's always new things to be discovered. There's always a lot of exciting work going on. But for the things that we're going to be talking about, for today at least, we're going to be primarily focused on the classical side. But, of course, with the advent of quantum physics, we got a lot of things like nuclear power. So we will dive into some of that material quite soon here. But for right now, start with the basics. So the name of the course is Energy and Environment. So I think it's probably a good time to start talking about energy. And there's a few different ways that you can actually define energy. But one of the good ways that we can consider right now is energy is the ability to do work. And at first, work is another question to say, okay, well, what is work exactly? Work, specifically in physics, is using a force, pushing something some distance. That's it. That's the whole thing. So when we're thinking about different types of energy, the ability to do work or anything else like that, how do these things actually compare? There's going to be some relationships that we need to talk about. But before we do that, I really want to nail down what we mean when we say some sort of force. right? And this definition, what we think of when we think of force, is certainly probably on the right track of things, right? There's no major corrections that I need to make on that one. There's not a fancy definition that we keep hidden away. It is some sort of push or pull. And we've got a special way of defining it in an equation. It is anything between two objects that causes acceleration. So I know we're kind of dumping a lot of terms here, but this will be the last one. When we have multiple forces acting on one object, so for example, right here, I'm sitting in place. Gravity from Earth, surely, pulling me straight down into the ground, but the chair that I'm sitting on exerts a force back up. And what that means is that there are multiple forces acting on me. The net force, the total sum, all forces acting on me right now, completely balances out. And I stay still. So something's not going to start moving just because it has forces, right? If all of those forces acting on it are kind of balancing out, then we don't get anything, right? That's what like a tug of war is. Tugging on some sort of rope, there's force on one end, there's force on the other end. When they exactly cancel each other out, the rope doesn't move. But if the force is greater on one side, then we start to get some sort of motion, and that's what acceleration is. Or more specifically here, acceleration is some sort of change to our velocity. So this is a little bit interesting, because if we're talking about changing a velocity, you might think of speed, and that is half of it. Velocity is speed and direction. Those two things combined together into one term. That's what velocity is. So if there is acceleration, there's a lot of different options. Affecting our speed, we could speed up, we could slow down. Sure. We could start moving, we could stop moving. Those are changes to our speed. But you could also change direction. You can maintain the exact same speed but start curving in one direction or another, and that is also an acceleration. So forces are involved with all of that stuff. There needs to be some sort of force to actually get that acceleration in the first place. And a quick check, if you're thinking about this, the three major parts of controlling a car, right? We've got the accelerator or the gas pedal, we've got the brakes, and we've got the steering wheel. Think about it for a minute, and maybe pause the video if you need to. Think, do these things cause acceleration? Which ones do? And if you're coming back from that brake, all three of these will cause some sort of acceleration. Now, I imagine a lot of the time, if you're thinking about something like the brakes, the word decelerate comes to mind. And that isn't really a term that we use in physics. I know it's a popular term to use just talking casually, but in physics, we typically think about that as a backwards acceleration. That is to say, we were moving forward. Now, we're starting to slow down. Our acceleration wants us to go that way, right? It's pointing in the opposite direction of our motion. If our acceleration points to the left of us, then we're starting to curve to the left. If our acceleration points to the right of us, then we're starting to curve to the right. And I know that I'm doing this all mirror, so I recommend do these hand motions with me. I do them for a reason. I think they help. But all three of these things are responsible for acceleration. In the case of the accelerator, it's acceleration forwards. In the brakes, it's acceleration backwards. And in the steering wheel, it's acceleration side to side. So, there are all sorts of forces, right? Looking at something like a car, it's a little bit hard to distinguish where those forces are coming from at first, but you have to consider here, anytime there is some sort of push or pull, that's a force. So the force of gravity is what's keeping you on the ground. Picking up a pencil, pushing a book across a table, those are examples of what we call a normal force, and I'll have some definitions for this in just a minute. But there are all of these different forces. Anytime that you're interacting with something causing some change in the motion, that's a force. And the unit that we typically use to describe that is something that we call newtons, right? Based after the man himself. If you do enough work in the field, you get something named after you. In the case of Isaac Newton, it was force. So in physics, well, really, reality, as far as we know right now, operates through four different fundamental forces. The big two that we're going to be mostly concerned about are gravity and electromagnetism. Gravity is, of course, what Earth is doing, keeping you stuck to the ground. Gravity is what is keeping the Earth orbiting around the sun and all of the planets for that matter. Gravity is what's keeping the moon orbiting around the Earth. For the most part, gravity is an extremely weak force. And that might not seem obvious at first, because gravity is like a really strong force according to you, right? Looking around, if I'm standing in place or if I try to jump up in the air, I can't really get very far. The Earth pulls me back down really, really quick. So surely the gravitational force must be at least kind of strong. Well, okay, put a pin in that. Let's come back to that in just a little bit here. Thinking about something like the electromagnetic force. Now, this is a little bit of a different story. What it is that there are some particles in the universe that have what we call positive charge, some objects in the universe that have what's called a negative charge. So if you remember anything from a high school chemistry course, electrons have the negative charge, protons have the positive charge, and there's other particles there, but those are the main big ones that make up atoms. So we'll focus on those. Now, if you're talking about something like lightning, for example, that's clearly electromagnetic interactions going on, right? A fridge magnet, it's got magnet in the name of it, it's surely operating through the electromagnetic force. But it's also what, well, 4 of the 5 of these forces are. See, what happens here is that generally, positive charges don't want to be around other positive charges. Negative charges don't want to be around other negative charges. The term opposites attract works really well in physics because positive and negative love to be next to each other. But positive and positive, or negative and negative, like charges, they're not fans of each other. And if you think about the structure of an atom, we've got that nucleus inside that's got all the protons and neutrons, that's got a really, really intense positive charge. Then there's this cloud of electrons floating around the outside. So a very positive core, a very negative exterior. Typically, we call atoms electrically neutral because that totally balances out. Whatever positive charge there is on the inside, there's a negative charge on the outside, and everything cancels out, and that's fine. But if you get too close to an atom, if you start to get really, really, really close to an atom with another atom, then those negative electron clouds don't really want to be next to each other. They've got some issues with that. And the proof of that is just that I can press my hands together and they don't just slide through, right? They get stopped. The atoms in one hand, all of those electron clouds are meeting the electron clouds of the other hand, and they're stopping each other. They're getting very, very, very close together, right? So close that we can't see anything because electrons are too small for us to see. But, sure enough, that's the result. So when you're standing on the floor, that's electromagnetic force. When you push on a wall, that's electromagnetic force. Your fridge magnet, that's electromagnetic force. And so, where's my proof that gravity is an extremely weak force? Well, the other 2 forces, let me get back to those in a minute, but one common example is that fridge magnet. Right? The really thin, cheap one that you probably bought for $5 as a souvenir on a vacation. Think about it like this. There is a force of gravity acting on that magnet. You can test that yourself. Pull it off, drop it. It falls, right? Nothing new for us. The entirety of Earth, all of Earth's mass, is pulling on that one tiny magnet, trying to pull it down to the ground. And when you stick that tiny magnet to your refrigerator, it completely counteracts all of the gravitational force from the entire Earth. Electromagnetism wins with nothing. A fridge magnet by itself completely overpowers all of the gravity on Earth. That's something, right? That's a pretty intense comparison. So gravity is actually, maybe a bit surprisingly, the weakest of all 4 of these forces. And I know that we have force number 4 is called the weak nuclear force, the weak force. Gravity is even weaker than that force. It is by far the weakest of the 4 forces. But unfortunately, when we were getting to the names later on, when we were discovering subatomic particles and things like that, I guess we ran out of creativity. right? Because we came up with the strong force and the weak force, and that's just kind of what we're stuck with. So these were forces that weren't discovered until much, much later, comparatively speaking. And the reason for that is because it's working on an atomic scale. In fact, these forces don't quite interact like the other forces do. The weak force and the strong force both, they are operating really only on the scale of the atom. They don't extend beyond a single atom. That's just too far of a distance for them. So they're things that we're never going to notice in a day-to-day life, but they are there. They're very powerful and very responsible for keeping everything together. If not for these forces, atoms would be constantly exploding all over the place. Everything would be a mess. Reality would not exist as we know it. So these forces are very, very important, but they're very tiny in size, too small for us to ever notice, not unless we know exactly what we're looking for. So, surely, if we're talking about the forces like this, and I'm trying to tell you that electromagnetic force and electromagnetism was not unified as a complete theory until, well, this was right around the turn of the 20th century, just a little bit before that, then surely we've been dealing with forces for a little bit longer than that. And that's right. We've actually got some more common names for a lot of these forces. Most of these forces are results of the electromagnetic force, but we've got some specific names for most of them. So gravity, still gravity. Nothing changing about that. Friction force is another example of the electromagnetic force, but it's looking at a specific case. Right? The friction force is any time you've got two objects trying to rub together. And what that is that if you get really, 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 really close, nothing is actually completely smooth. There are all these jagged edges if you zoom in far enough. And those jagged edges just kind of catch on each other. So when you're trying to move something, that friction force is quite literally all of those things just colliding and jostling about and has to kind of get over that hump to make what this happen in the first place. Anytime two objects are trying to slide past one another, that's friction. There's some other strange examples of the electromagnetic force, whether or not you realize it. Digesting food is a fantastic example, right? Because there are these long carbohydrate chains in the food that you eat. And what happens with that is that on its own, it's not very useful for our body. So our body breaks that down through these chemical processes, right? And that's electromagnetic force. That's atoms, the individual electrons and the protons all interacting with one another, trying to do all of these different forces, turning into new compounds, and that's all a result of the electromagnetic force. Common examples, surface tension, another fun example, right? The polarity of water, if you know anything about that. Magnets, of course, part of electromagnetism. And there's all sorts of things. So some different examples we might see on this one. These are just some common examples where a lot of these forces might show up. But we don't need to, I think we've covered these examples well enough at this point. So we got into all of this discussion in the first place because I was trying to come up with some sort of definition for work. So let's get back to what work actually is. So I said we need to exert some sort of force over some sort of distance. That is to say, I need to push something somewhere. If I push on something and it doesn't move, I didn't do any work. It has to be moving. But even more specifically than that, not only does it have to be moving, but it has to be moving in the direction that I'm pushing. So when we look at this equation here, what this is force times a distance times cosine, the trig function, of an angle, theta. And this force is acting up and to the right. But the box is sliding to the right. The box isn't traveling upwards, it's sliding to the right. So the cosine of theta is basically saying don't take the whole force, just take the part that's going to the right. Right, if we think about it like a triangle, that's kind of what it looks like, right? We can break this triangle up. We've got a right triangle now. We've got an upwards component. We've got a sideways component. Cosine of theta is taking only that sideways component. Only the force going in the direction of the motion. So if you're pushing just directly horizontally, a cosine of 0 would be a cosine 0 is equal to 1 would just be the full force, force times distance. If you're pushing straight down into something while it's trying to move, well, you're really not helping move that, are you? You're just pushing down onto it. So in that case, you're not contributing any work. So it's always based on the direction of the movement and how the force compares to that. So you can think about this. Am I doing work pushing a wall? If I lean into this wall right next to me, I'm not moving, the wall's not moving, but I'm certainly pushing on the wall, no work's being done. If I push a book along a desktop and take some objects around the house, I'm not going to do this because it's going to scrape really bad on the mic, but try this out, right? Push a couple things around on your desk. Have some fun with it. Make a little bit of a mess. Are you doing work? Of course. Right? That whatever it was on your desk, that pen or that water bottle or that notebook, that was completely stationary before you had any meddling with it. And as you were pushing it, it was moving how you were pushing. You were doing work. You were putting energy into it. If I hold a book, or in this case, I've got my trusty water bottle, if I'm holding this water bottle, what do you think? In this case, I am exerting some force. If I let this thing go, it wants to drop to gravity. So by holding this thing up, I am indeed exerting some upwards force counteracting gravity. But since we're not moving anywhere, no work is being done. Work is not done until I start lifting. When I lift it, work is done because now there's motion, the force and the direction of the motion, that's work. So, here's what we see. In all of these cases, we need some distance. If there's no distance, if there's no travel, there's no work. So, some questions then to think about here. Let's imagine we've got two people pushing on a car, but they're pushing in opposite directions. So this car is moving to the right, and let's say that it's moved 2 meters. How much work does person A do? Got a couple different options here. Pause the video or take a minute to think about it. What I think about in this case, there is 500 newtons pointing directly horizontally, right? That is to say, none of the force is being wasted, right? There's no up force, there's no down force. It's all being pushed in the direction of the motion. So I don't need to worry about splitting up an angle, or if we want to be rigorous with it, right? It's an angle of 0 degrees. So it would be force times distance times cosine of 0, which is just 1. Force times distance, 500 times 2. We should be expecting 1,000 Newton meters of work. So now let's look at this. How much work is person B doing? Now this one's a little bit strange, because at first you might look at this and say, hey, wait a minute. They're not exerting a force in the direction of the motion. They're exerting a force opposite the motion. What do we do about that? Well, there's a couple ways to consider it. Again, if you really love trigonometry and you think of unit circle and that's what you stick with, great. Then you need to think about this. The angle is 180 degrees. The force is going one way, the displacement or the travel is going another. There's an angle of 180 degrees between those two, and 180 degrees plugged into cosine gives us -1. So that would be force times distance times -1. The way that I personally like to think about it is the car is trying to move to the right. The person, or rather person B, is trying to stop that motion. Any energy that that car has, person B is trying to take that away. So that would be negative work, work leaving the car rather than going into it like person A is doing. So in this case, we're going to be seeing a -600 Newton meters. So we can think about net work being done, and not networking, but a net work is a total sum of all of the work being done. In this case, I would take the 1,000 from the first person, the -600 from the second person, for a net work of 400 newtons per meter, or yeah, Newton meters is what I should be saying here. Or if you want to think about it a slightly different way, the net force acting on the car, there's 500 newtons to the right, 300 newtons to the left, so that is a net force of 200 newtons to the right over a distance of 2 meters, still get to 400. In physics, oftentimes you'll find that there's more than one way to do a problem, and any way that you approach the problem should land you with the same answer. It's a good way to check to make sure that you did something right. If you can do it a second way and still get to the same spot, you're probably in a pretty good place. So, how does this work actually begin to relate to energy, right? That thing that we're supposed to be focusing on here. Well, generally speaking, there's a few different ways that energy can be, but one of the most common is kinetic energy. That is, moving things have some energy associated with them, right? Surely it takes fuel, it takes energy to get a car moving. It takes energy to get you out of bed. It takes energy to lift something up. It takes energy to turn on a laptop or a phone. Kinetic energy is the energy associated with the movement in all of those pieces. And I know the movement is not necessarily obvious in all of those, but even in the cases of looking at something like electronics, there's still movement going on the inside. You've got the fans, you've got the electrons moving through the wires, you've got a lot of different pieces that are moving, even if they are really small. Everything that is moving has a kinetic energy, and that kinetic energy is calculated by 1/2 times the mass of that object times the speed of that object squared. So speed times speed. Speed is a little bit more important than mass and kinetic energy. Both are certainly factors, of course, right? If we're comparing the kinetic energy of a bicycle versus a car versus a semi-truck, right? Kinetic energy goes up in all of those cases, assuming they're at the same speed. But if I'm looking at a car going 20 miles an hour and a car going 40 miles an hour, the car going 40 miles an hour actually has 4 times as much energy because of that v squared. So work is most typically thought of as a change to this kinetic energy. And hopefully that makes a little bit of sense, because when we're thinking about work being done, there needs to be some distance covered. There needs to be some movement. So if work is being done, there better be some sort of kinetic energy because there better be some sort of movement. Otherwise, we never really had work in the first place. Work from gravity is actually given a special name. Gravity is a force, right? If I drop an object, then it falls some distance. That entire distance, it had the gravitational force acting on it. So the force of that, or more specifically here, the energy associated with that, is what we call gravitational potential energy. Not just gravitational energy, gravitational potential energy, because of what we're doing. Let me take a highlighter, for example, because if this thing falls to the floor, I don't care too much. If I take this, it is suspended in the air, right? Some distance above the ground. Right now, it has that gravitational potential energy. And it's called a potential energy because it's work waiting to happen. This thing has no work being done on it yet. But if I drop it, now gravity does that work. It accelerates it, it falls down to the floor. To give that energy back, something else needs to do work to raise it back up in the first place. But as soon as gravity gets the chance, it gives it all back. It converts all of that right back to kinetic energy. So the way that we calculate that is this equation mgh, where m, just like before, is still the mass of the object, h is the height up, and g is what we call Earth's gravitational constant. It's a number that we've got calculated out for us already, 9.8 meters per second squared. So, let's imagine some scenarios here. An object with 2 kilograms of mass is lifted into the air by 4 meters. First, what is the potential energy of that object at the very top? Second, what is the kinetic energy at the bottom of the fall? What is the final velocity just before it hits the ground? So I'd highly recommend pausing the video right here, working through this problem, or at least thinking on it for some time. Welcome back from your problem-solving session. Looking at this thing, what we're starting with, we're lifting this into the air. That tells me gravitational potential energy. Something higher up has more potential energy, so if we've lifted this, potential energy it is. mgh means we're going to take our 2 kilograms times the 9.8 times 4, or 8 times 9.8. That means we have a total of 78.4 joules of energy at that height. Now, that object is dropped. You've probably heard of something like energy conservation before, right? This idea that energy can't be created, nor can it be destroyed. It can only be transferred from one place to another. And that's exactly what happens here. Remember, gravitational potential energy is work waiting to be done. That is to say, once released, once given the opportunity, gravity will give all of that energy back. It will do all of that as work, and work is changing kinetic energy. So let's think about it like this, right? We lifted this thing all the way up, we release it. Halfway down, it's still some height above the ground, right? We're still a little bit up there. We're still 2 meters above the ground. Half of our energy is now potential energy, but because energy can only be transformed, it can't be destroyed, half of it is now kinetic energy. That means by the time we're right at the bottom, right before we hit the ground, all of our potential energy has been converted into kinetic energy. That is, we're right back to 78.4 joules. 78.4 joules never changed. That was our total energy the entire time. When we actually think about the final velocity now, what we can say is all of that energy is kinetic energy. We know the mass is 2 kilograms. So we have 78.4 for kinetic energy, 1/2 times the mass of 2 kilograms. Solve out for our speed. And when we solve out for that speed, we should see a final speed of 8.85 meters per second, right as we hit the ground. So let's look back at friction again. Friction always opposes motion, and it's always existing between two objects trying to slide past each other. And there's a way that we calculate this, but it's a little iffy sometimes, right? There's not necessarily one concrete number, not the same way like there is for potential energy or kinetic energy. When we're thinking about friction, we have these two terms. We have mu, what we call the coefficient of friction, and the normal force. So the normal force is any force between two objects. There's a normal force pushing up on me right now from my chair. If I lift up my highlighter one more time, there is a normal force from each of my fingers acting on this thing. Anytime two objects are touching, that's a normal force. So we take that normal force, we multiply it by this friction coefficient, which is anywhere between 0 and 1, and that's our friction force. So let's think about this for a minute. Friction is a force, and it typically acts on any objects moving against each other. So if friction is, generally speaking, trying to stop the motion, then friction is always doing negative work, taking away that kinetic energy. The question then, where does that energy go? In the case of gravitational potential energy, surely gravitational potential energy we release falls back down to the ground. It's kinetic energy now. If we lift it back up, it's back to gravitational potential, right? Energy has a concrete form that we can see the entire time. And actually, it's so special that we call that mechanical energy. Friction doesn't play by those rules, though. But the energy can't be destroyed, so the question really is, where does it go? Here's a good way to find out. Imagine you're trying to warm up your hands, right? Put your palms together and just rub them back and forth a little bit. What's going on? Well, for one, I can hear my hand sliding back and forth. That is to say, there's some sound being created by that friction. Second, I do feel a little bit of warmth on my hands. Not a lot, but a little bit. So that tells me maybe some of that energy is heat. The third place is a little bit less obvious with your hands, but it does show up if you're thinking about something like sandpaper, and that is breaking the bonds of atoms, or rather wearing away at whatever that friction is acting on. Right? How many of you have ever run into the circumstance you're trying to move some sort of furniture and it's just maybe dropped a little bit too much, or you should have lifted up just a little bit more and you notice a gouge in the floor? Yikes. I know it's happened to me before, right? That's friction. Gouging the floor, removing those top layers of atoms, that was friction. There had to be energy to do something like that. It doesn't normally happen. We have to do energy, take some sort of energy to actually remove those atoms. So those are the three big places that friction usually deposits that energy. And we usually consider this lost energy because when we're thinking about something like mechanical energy, motion to motion, fantastic. Potential forces or potential gravitational energy, other potential energies actually beyond just gravity, all of those things transfer one-to-one perfectly fine. But friction, when you put that energy into heat and sound, you can't really get that back, right? The heat and sound from running a car, you can't use that to run the car. That's exhaust now. That's out into the world. It's not coming back into the car. So friction is what we consider to be a non-conservative force. Because unlike gravity, when friction does work, it never will give that energy back. Whereas gravity will. Gravity, we put some energy in to lift something up. We'll go with the marker example again. I lift this thing up. Gravity the entire time is pulling down, doing a negative work on this marker. But when I drop it, it's more than happy to give that energy back. Friction does not do that. So, and one other thing, to kind of show that the friction force gets enhanced. Go back to this example one more time. Just rubbing your hands together. Now what I want you to try to do is press a little harder, right? Put a little bit more force between your hands, and you'll notice a couple things. First, it takes a lot more energy, right? Your arms can't nearly as easily do that. Why is that? First, well, they're fighting against the friction, right? The more they have to fight against the friction, that's more effort from your arms, more force from your arms to counteract that friction. That right there is directly the normal force increasing, and so the friction force increasing. But second, the other idea behind this is that when you do that, when your arms are putting in that extra bit of energy, well, now they're putting in more force over the same distance, which means more work. More kinetic energy goes into your hands. More kinetic energy that's sapped away by friction. And that's why you notice the sound changes a little bit, but especially the biggest change that I feel is that my hands are noticeably warmer after doing that. Just for a couple spans back and forth, I really start to feel that heat between my hands. So, think about this problem for a minute. Let's imagine I'm pushing some sort of book across a desk, 2 meters, and I have to exert 20 newtons of force to do that. When I finish pushing, the book is completely still. So I've just kind of slid it over to the side. Try this yourself, right? Wherever you're working right now, move something a little bit, push it, and then watch it for a minute. That was an exciting watch, I'm sure. Unless you push that something off of your desk, in which case you're probably scrambling right now, so I'll give you a second to rewind. But if you kept it on your desk, then nothing happened when you stopped pushing. That was it. That's expected. That's what we're used to on a day-to-day basis. But what's actually going on there? Well, you certainly did some work pushing that book. You exerted a force over a distance. So why didn't the book have kinetic energy? Why didn't it keep moving? Because just as you were putting energy into the book, friction was taking that energy back out. And they weren't exactly equal in the race, right? I want to keep that in mind. While you're pushing the book does have some kinetic energy. So right there at the beginning, you get an energy head start on friction. But now, friction catches up. Friction is balancing out with that. As soon as you stop pushing, friction takes that last little bit of energy away. That is to say, any work that we did to move the book is exactly the same amount of work that friction did on the book. So if our work was supposed to be 2 times 20, a total of 40 joules, friction also did 40 joules. But there's one thing to keep in mind here. It's not just 40 joules that it did. What it really did was negative 40 joules. It took the energy back out of the book. So, to recap here, there are a couple different ways that energy can exist, right? Work is energy that is kind of in transit. Something is giving something else energy. But once that thing is moving, it has kinetic energy. Now, if you've got some common forces, like gravity or electromagnetism is another example of a conservative force. In a case like that, you are storing some work to be done later. Other places it can exist, though. Chemical energy, which, to be honest, is actually just electromagnetic potential energy again. But we do think about this a little bit differently, right? Because generally speaking, when we're thinking of different things that exist, batteries are a fantastic example. What makes batteries run is a chemical reaction inside of the batteries. Certain compounds going through some sort of reaction becoming new compounds. And in doing so, energy is released. So it starts as chemical energy, it is released into some other form of energy. So for example, burning methane, this is the chemical equation for methane burning. C2H4 combined with a little bit of oxygen, that's what we get for something burning. We get carbon dioxide, we get a little bit of water, and in changing those compounds, energy is released as heat, which is thermal energy. Thermal energy, this is a fun thing, and it's not temperature. I do want to keep that, I'll talk about an example here in just a minute. Thermal energy is actually kinetic energy as well. Something that's hot, or rather just thinking about the temperature difference of one single object. What's happening there is that when that object is cold, the atoms are buzzing around, but they're a little bit sleepy, right? They've got a set location that they would like to be, and they kind of just patrol around that area, buzzing about randomly. When that object gets hotter, those individual atoms start buzzing more wildly, very quickly, vividly, going all over the place. The hotter something is, the more intense the buzzing of the atoms, right? It never goes away completely. There's always a little bit of buzzing of the atoms, but the colder something is, the less buzzing, the hotter something is, the more buzzing. So really, it's kinetic energy, but just kind of like on a more microscopic scale. Not the whole object moving in one way, but all of the individual atoms making up that object moving around. So how is temperature actually different from heat? Well, here's the example to think about. You have probably prepared pasta at some point, or at the very least, seen it prepared somewhere, right? You start with a big pot of boiling water. You might have also made some cup ramen, right? We're in college. I know how these things go. The amount of energy that it takes to get those two things to their boiling point is quite different, right? That shouldn't be surprising. For the cup ramen, you only need to boil a little bit of water. It doesn't take that long. You might notice this as well if you've ever worked with a kettle. The more water's in the kettle, the longer it takes to get up to that boiling point. At the end of the day, we want the same temperature, but the heat required to get up to that temperature very much depends on how much is there that we actually need to get up to that temperature. We'll talk about that in a little bit more specific detail later on. Not quite yet. We'll come back to that. So, I know we talked about energy servants quite a bit here, imagining like if we had people sitting around doing work for us to try to run all of these things in our day-to-day lives, what would that actually look like? Well, first, it starts as a food energy, a chemical energy. You eat something, your body has to process that. It takes those, grabs the carbohydrates that it's interested in, and waits, holds on to those things. When your muscles are called upon, it will burn those carbohydrates or use them in chemical reactions that release energy. And releasing energy is how we get to kinetic energy of the muscles, right? Full arms moving rather than individual atoms. So now our full arms are moving, but we have to turn some sort of crank. So we go from kinetic energy in the arms to kinetic energy in the crank. Kinetic energy in the crank has to be turned into electromagnetic energy inside of the wire. Finally, the electromagnetic energy inside of the wire passes through the light bulb, comes out as light, comes out as heat. So some of the examples that we can see for this are a little bit more simple, right? If we're thinking about something like a furnace, that's a nice and simple one. We start with natural gas, we burn it, it's heat exactly as we wanted it, right? Very few steps, one single step, going from fuel to end. Perfect. Most things are not so simple, unfortunately. Most things are a little bit more like this, where we've got all these individual steps. And we also run into a little bit of an issue as well, because the more steps there are, there's a little bit of energy lost in every single one of these steps. And again, energy loss doesn't mean energy just evaporates. It just means energy goes in places that we really don't want it to be, right? If you've ever done a workout, you'll know this, that you start to feel warm afterwards. So the useful energy, the intended energy, was going onto the elliptical or going on the treadmill or lifting the weights. But the lost energy, the energy in excess, the ones that we didn't want to lose, that's coming out as sweat and heat, right? Your body generates a lot of this extra waste heat that we really didn't want in the first place. And so now it's trying to get rid of that. That's energy lost in that step. If we're thinking about turning some sort of gear, there's a little bit of noise associated with that. If you've ever spun a gear too fast, you know it starts to get a little bit warm as well. So again, there's heat, there's sound, there's waste energy. Not that it's going, into the void, but that it's turning into a form that we really can't make any use out of. So, I think what I'm going to close out with right now are some tables. I'm not going to talk through these necessarily, but this is a small variety of different values, different units that are commonly used in different places. And you can kind of start to see the comparisons of a lot of these different units as we use them, right? Like some of your day-to-day units like horsepower, when you're thinking about car engines, what does that actually compare to a watt? What's that ratio? We've got some comparisons here. But for right now, I think we'll close this one out. Next time around, the schedule got a little bit messed up. We had a pretty snowy day at the end of the week of week 2. So the next lecture is actually going to be our first step into lecture 3, or into the week 3 material, but it does start with a little bit more of the section 2 stuff. So be on the lookout for that. But that's all we've got for right now. I'll see you again next time.